Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the last module for this week, this module 3.6. And I guess we are now sort of ready to sum up what we have been doing these last 2 weeks, because basically what I've been trying to get across is this general method for handling quantum transport problems, where the basic input is this H and the sigma. And once you have those, there's a straightforward way of calculating things like electron density, density of states, current, etc. And in the last module, I specifically talked about how to include magnetic fields, because I was thinking of using this example of current flow in a high magnetic field. Again, not because, as I mentioned, it's not because it's of great device importance, but because it illustrates some very interesting physics, and also it was the first context in which this quantum of conductance was actually experimentally observed. So the problem we are talking about, if you remember, is this conductor in which current flows from left to right, and you have a magnetic field. So if we go with like X and Y, and you have a magnetic field out in the Z direction. Now, what is observed is that when you have a current flow in this direction, of course, there is this Hall effect. That is, there is a transverse voltage. And as I mentioned, that if you look at the ratio of that transverse voltage to the current, that's called the Hall resistance. And it showed this amazing quantization, actually. And that was observed back in 1980, several years before the quantized conductance in ballistic conductors was observed, which was like 1988. Yeah. Anyway, so first, of course, how would you set up this problem? How do you actually calculate this resistance, or how do you model something like this? Well, the starting point is you have to set up the Hamiltonian, and as I explained, the Hamiltonian can be viewed as these alphas, which represent one column along the width, and then connect it to the next column by these betas. And once you have that, you can calculate the sigmas. How do you write the Hamiltonian? Well, that's what we did in week 1 in general. What I did in the last module was to tell you how to include magnetic fields into the Hamiltonian. Okay? So let's say we have all that. And now we go ahead and look at the density of states. And by density of states, what I mean is this quantity here, the A. That's what's called the spectral function. It's a matrix, but if you look at its diagonal elements, it tells you the density of states. And of course, once you have H and sigma, there's a straightforward prescription for calculating that. Now, when you calculate A then, you see, in a problem like this, when you calculate it, the density of states, you'd find that along the X direction, it's the same everywhere, because this is a uniform conductor. On the other hand, along the Y direction, it's not the same. It varies, it could vary in this direction. So often, it's convenient to do what you might call a grayscale plot. That is, let's say this direction is Y, and this direction, of course, here, this direction is another spatial direction, X. But X has not much information, because nothing varies with X here. It's a uniform conductor. So what you could do is use this axis as energy E. And then do a grayscale plot, in the sense that when I look at the density of states, which means if I'm looking at the density of states at a location Y at an energy E, how will I find it? Well, I find it from that spectral function A. I look at its diagonal element and at this energy E and divide by 2 pi. So if I do that, I'll get this density of states. And the way I could plot it on this two-dimensional picture is, I could say, well, whenever it's big, I'll make it white. and whenever it's small, I'll make it dark. That way you'll have what you call this grayscale plot. Or you could be more colorful, put in red and blue if you like. But if you do that, one of the first things you'll notice is you'll see on the energy axis, there'll be white streaks. Maybe I'll use a red for this. You'll have white streaks like this. And then another one here. And then another one here, equally spaced. Okay? Now, here of course I've drawn Y and E, because Y is along the width direction and the energy is along that direction. You may need a little adjustment because usually we have been drawing E in the vertical direction and so from that point of view you would have wanted to draw Y along this direction. And in that case, these energy levels would have looked like this. Okay? So equally spaced in energy, but so this and this are basically the same picture. You see, and I was not quite sure. I was in two minds as to which one to use, because if I used it this way, then the energy would be vertical like we have done throughout the course. Whereas if I do it this way, then the Y direction corresponds to the width of the conductor like we have been doing. Anyway, so as long as you understand what we are talking about. So let's go with this picture then. So question is, why do we have these evenly spaced levels? And these are what are called Landau levels. And let me explain briefly where it comes from. The idea is that inside the solid, when these electrons are moving, so let's say an electron is moving in this direction. Now, when you have a magnetic field, there is a force on it, which is this V cross B. So what that makes it do is, it makes it curve, like so. And what it does is it goes round in a circle. And what is the radius of this circle? Well, you could do a semi-classical analysis. Semi-classical means where you're thinking of electrons as particles. Of course, the right way to do it is you go to the Schrodinger equation and actually find the energy levels. What I'm trying to describe to you is a simple heuristic picture for this. So you could say, well, it's going round in a circle. What's the radius of the circle? Well, you could say that the mv squared over r, that is, if it is going round with a velocity v, then the centripetal force should be equal to this Lorentz force. Lorentz force meaning this QVB. So this is the force the electron feels due to the magnetic field. And that force should be balancing this force of providing this centripetal acceleration which is needed to make it go around in a circle. Now, and this force is, of course, perpendicular to the direction of the velocity. So just like what you need to make something go in a circle. Now, if you do that, then you get this simple relation that R is equal to P over QB, where P is the momentum. Now, this tells you that you could have electrons going round with different momenta, and depending on what the momentum is, there will be a certain radius. So, bigger momentum will have a bigger radius. Okay. Now, to this you could add a little quantum mechanics, or this wave nature of electrons, by saying that, well, you cannot have electrons going around in any circles of arbitrary radius, because what must happen is that the electron wavelength must fit into this circle. This is kind of the argument that Niels Bohr used to develop this Bohr model of the atom, before quantum mechanics came along. So the Bohr model was like 10, 15 years before that. And the argument was something like this, that this wavelength has to fit in. So you could, if you use that argument, you could write, so let me write that down, 2 pi r, which is the circumference of this circle, that's equal to some multiple n, some integer, times the wavelength of electrons. And wavelength of electrons is nh over p. So this is what came from just Newton's law, equating the force to the Lorentz force to the centripetal force, that's acceleration. And this comes from wave nature of electrons. And if you combine those two, you see, you'll find that not all momenta are allowed. Only certain specific momenta p would be allowed if you combine those two. And the way you can do it is, I suppose I could take this 2 pi from here and make that h bar. H over 2 pi is h bar. And then you see, well, you could say, well, this is equal to that. Okay? So what that tells you is, since both are equal to r, that tells me that p squared, so nh bar over p is equal to p over qb. So I could say p squared is equal to n times h bar qb. So only specific momenta would be allowed, Pn, corresponding to different values of that integer. And then I could find the corresponding energy, En, by taking Pn squared over 2m. P squared over 2m is like the energy. So that gives me N times h bar times qb over m. I guess I had a 2 here, so I'll put that 2 here. Okay. Well, and this is roughly the right result except for a factor of 2. This is a very simple argument, and the basic fact is then that electrons in a magnetic field have energies that are integer multiples of a basic quantum, and this is this h bar qb over m. qb over m is what's called the cyclotron frequency, omega c. And so it's half h bar omega c times n. Actually, the levels that you see are not spaced by half h bar omega c, they are actually spaced by h bar omega c. So one of the first things you could check easily, and the numbers are in your notes, you could check easily is that in this calculation, whatever you're getting straight out of using these NEGF equations, you'll get these streaks, these discrete levels, evenly spaced, and that spacing corresponds to h bar omega c, where omega c is, as I explained, equal to qb over m. Depends on the magnetic field. So you'll get that. That's nice. Now the next thing you'll notice, if you look at this density of states carefully, is that if you go near the edges, actually these levels sort of curve up. So what I mean is these white streaks curve up like so. And let's do the same here at the two edges. So one way to think about it is that, well, when you get to the edges, there is this big potential that is keeping the electrons inside. You see, the edges represent the boundaries that the electrons cannot cross. And the way the boundaries kind of keep the electrons in here is because there's a potential there. So it is as if an electron is right in the middle somewhere here, it has a certain energy, but then once it gets near the edges, the energy increases. So you could think of it as if these represent this increase in energy because it feels the effect of the boundary. And so you'll see these, what are called edge states actually. So around these edges, you'd have these states. And so if your chemical potential, say, happens to be here, then the conduction would be, of course, the one point we have discussed throughout this course is that conduction is due to energy levels right around the chemical potential. So if your chemical potential, let's say, happens to be here, then you'll have these three states on one side and these three states on the other side, which would be where electrons would be conducting. Okay. Now, the one interesting thing, though, that you'll see, it's like this. What I've plotted here is what you'd see if you plotted this density of states. But supposing we now do a transport calculation, that is a current flow calculation, where we assume that on the left contact, we have F1 equals 1 here. Let's say F1 is equal to, let me get a better pen. So if F1 equals 1 and F2 is equal to 0, which means we are thinking about an energy at which the states in this contact are all full with electrons which are coming in, and here it's all empty. They just go out, nothing goes out there. And if you looked at the density of states, of course, that would still look exactly like what we discussed. But supposing we look at the electron density at that energy, that's this Gn. That is, when you look at A, that gives you density of states. When you look at G super n, this quantity here, when we look at G super n, the one that's given by equation number 2, that is like the electron density. So when you look at that, what you'd find is something interesting. And that is, you would only see one edge. So let's say, you wouldn't see this part at all. You'd see only these. So if you looked at the Gn, you'd only see these states on this side all occupied with electrons. So it is as if when the electrons come in, they only occupy states here and not here. On the other hand, if you had turned it over and had electrons come in from there, then you would have seen electrons actually go into that edge. So the idea is that with these high magnetic fields then, it's as if electrons follow these edge states, and the states at this end are taking electrons in one direction, states at that end take it in the other direction. And these are called these edge states, as I mentioned. And often the way you visualize it pictorially, the semi-classical picture is something like this. That when an electron comes in from here, of course, because of the magnetic field, its path curves down and it hits the wall. When it hits the wall, it gets reflected back again. And again, it bends because let's say the magnetic field is such, it always makes you bend to your right. So it goes this way and it hits again. And then again, it comes back up and hits again and so on. So these are what are called the skipping orbits. So you have this electron then basically just hugging this edge and going down. That's the semi-classical picture, the particle picture that people have in mind for explaining why you have these edge states. And so you have these edge states here. Same at the other end, except that now they're going this way. So what that means is that because of these edge states then, at these energies, actually anybody going to the right is over on one side of the sample, anybody going to the left is over on that side of the sample. And the remarkable thing then is that you see you have what you might think of as a fantastically ballistic conductor. You see, usually ballistic conductor means that you're going straight in this direction, you don't get reflected. And ordinarily, of course, in any conductor, there would always be some amount of reflection. It would hit one defect or something. But in a situation like this, you see, electrons cannot be backscattered. Because even if there's a defect here, well, there is no way the electron can go backwards without transferring to the other side of the sample. And as long as this sample is reasonably wide, it's not easy to jump over to the other side. So the only way you can turn around is if something catastrophic happened that actually forced you to go there. Ordinarily, of course, it would be right here. And even if there are some imperfections here, defects or anything else, that's fine. It will just keep going anyway. And so you have this remarkably ballistic conductors. And naturally then, what happens is, when you look at the current carried by something like this, or the conductance, the current over voltage, it's like Q squared over H times the M, and M is the number of edge states basically. See? And there's usually also this 2 because of spin, which we haven't brought in at all in this. That's something we'll talk about next week. So this is the 2Q squared over H, but then there is this M, which is the number of edge states. I guess the way I'd put it is M is equal to 2 times the number of edge states. So if the way I've drawn it, if it was here, it would be 3 of these times 2, so this would be 6. And then if instead the chemical potential happened to be here, then you would have 2 edge states. And if the chemical potential happened to be here, you'd have only 1 edge state. And so now you might say, well, but we are talking about this voltage. I thought we had earlier said something about the Hall resistance, because after all, the Hall voltage is usually measured between this end and this end. But the thing is that because electrons are kind of going down this way, if you actually looked at the potential profile of how the chemical potential varies, what you'd find is that if the chemical potential here is 1, it's actually 1 all the way along the edge. And if it's 0, it's actually 0 all the way. If it is 0 here, it's 0 all the way along here. So it's like 0 here and 1 here. So if you measure the transverse Hall voltage, what you basically get is just the Hall voltage, just the total voltage between the contacts. And so when you plot the Hall voltage divided by current, which is what you call this Hall resistance, as a function of magnetic field, at first it starts out linear. That's the low field Hall effect. That is, when you have small magnetic fields, there is a little bit of a potential difference, and which increases linearly with magnetic field. But the thing is, once you get to these high fields where edge states can form, and you have this fantastically ballistic conductors, you actually see quantized things like this, which are given by h over q squared, which, as you know, is like 25 kilo ohms, and then 1 over m, and this m is like 2 times the edge states, number of edge states, 2 being due to spin. And you'd see these plateaus. And of course, what was extremely surprising when it was first discovered was how precise those plateaus are. And from this point of view, you say that the precision of those plateaus comes from how fantastically ballistic this is, and which is simply because you have this divided highway. Anybody going to the right is on one side of the sample, anybody going to the left is on the other side of the sample. Okay. So this I kind of use this example, as I said, for 2 reasons. See, one is that it's a very important effect, and which is now very well established, and it was the first experiment, I believe, where this quantum of resistance or quantum of conductance appeared, I think. Now, but the second reason also is, I wanted to illustrate how you could use this entire quantum transport method that we have discussed to enhance your understanding and intuition. So what I mean is, ordinarily, if you have taken a course on how electrons behave in magnetic fields, you'd of course have solved the Schrodinger equation, known about Landau levels, etc. But another way to approach it would be to say, well, let's use this. I don't know much about this, but I know how to put magnetic fields into a Hamiltonian. We know how to set this up. And once you have a code set up, you could easily put in a magnetic field, change magnetic fields. So sort of like a do-it-yourself quantum mechanics. You can try all this out yourself. And if you have done this right, you should get plots like this. And then you could say, well, let's see if we can understand this. Why are we seeing sharp levels? And then we can think about this, see if the distances are correct, and so on. And so an important phenomena like this, this quantum Hall effect, as I said, of course, was discovered experimentally. But if you never knew about that, for example, and you just set up this numerical model and you calculated, you would see this. And then one could try to understand those things. So the point I'm trying to make is that this method, which wasn't quite there 20 or 30 years ago. 20 or 30 years ago, firstly, computers weren't big enough. And so you couldn't have handled conductors that were big enough to be interesting. Because as you realize, the bigger it gets, the bigger these matrices get. And the bigger the matrices get, of course, it gets harder to actually do the numerical calculations. But today, with today's computers, I'd say 100 by 100 or 1000 by 1000 matrices are relatively routine. It's when you go bigger than that you need special techniques. But you can just do it on your laptop fairly easily. So that's one thing. But the other thing is this whole formalism, this whole method, as I mentioned, this whole set of equations, which have been known, as I'd said earlier, because original equations were due to like Keldysh, Kadanoff, Bain back in the 60s. But much of that is not widely known because it is couched in this language of many-body perturbation theory, whereas what we have done is done this from a one-electron point of view, one-electron Schrodinger equation. And as you know, there are all kinds of effects that are due to what you might call one-electron effects. And then there are many effects due to many-body interactions. There's many electron effects. And the latter are, of course, much more difficult, much more subtle, much harder to predict. And usually what happens in quantum transport theory is that people start from this general theory which has all these interactions in it, and then throw away the many-body interactions to get the one-electron part. On the other hand, I guess what that means is that whether you are talking about a many-electron effect or a one-electron effect, the theory looks equally complicated. On the other hand, a lot of steady-state transport usually can be understood within a one-electron picture. I mean, not everything. There are other many-electron effects that also have to be accounted for. But there is a large number of one-electron effects which can be understood in terms of this one-electron theory. So, for example, what I just described to you is called the integer quantum Hall effect. There is another vast field called the fractional quantum Hall effect, which arises from the formation of a very interesting subtle many-body state, which, of course, as it stands, won't come out of these equations. On the other hand, the integer quantum Hall effect will naturally come out of it. And what it does is gives you a straightforward way of treating quantum transport, at least including the one-electron effects, in a clear way. See, in a way that is predictive, and you can study all kinds of different things. And there's lots of interesting experiments now going on that one could try to understand using this. And what we'll do in next week is we'll look at spin-related phenomena, which again is another example of something where you can develop your intuition, where you can use this whole formalism to look at different things and develop your intuition about how spins work.